We've previously discussed the components of a single iteration of the learning process. In this lecture, we will gain a better intuition of what is happening during the backward pass. Our objectives are as follows. Understand the backward pass, or backpropagation, as a means of most efficiently updating our weights and biases to make incrementally better predictions. We'll introduce the mathematical concept of the gradient in an intuitive fashion and understand that the gradient of a function points in the direction of the greatest change in output of that function. Lastly, we'll understand how the gradient is used to most efficiently update our weights and biases, using a process called gradient descent. As a reminder, we will be discussing this portion of the learning cycle. Let's begin by transporting ourselves to this three-dimensional space. Imagine yourself standing at the top of this surface. Your coordinates in this space are indicated by W, B, and J. J represents the value of the cost function for a given W and B. Note that the value of J indicates how high you are on the surface. Now you don't like heights much, so you'd like to end up here, which is where the cost has reached a minimum. You'd also like to get here as quickly as possible. Let's be more specific. For each step you take on the surface, you'd like that step to be in the direction that allows for the greatest descent down the surface. Let's first try a naive approach. We'll randomly vary our weights and biases and see if we can get to the bottom. Clearly, this is not the most effective solution. Let's start over. Again, your height on the surface is the output of the cost function for a given W and B. To decide how to step in the direction of greatest descent, we'll need to figure out how the cost changes with respect to a small change in W. The mathematical object which captures this idea, that is, how the cost function changes given a small change in W, is the partial derivative of J with respect to W. We'll also need to figure this out for B. Let's now package this information in a succinct fashion, specifically in a column vector form. This vector containing the partial derivatives of J with respect to each of the parameters is called the gradient, which is signified by this nabla symbol. The gradient points in the direction of the greatest change in output of a function, in this case the cost function. Because we wish to descend down the surface, we use the negative gradient. What does it mean to use the gradient? In order to descend, we first calculate the gradient for our current W and B coordinates. We then individually update W and B by subtracting the value of their respective partial derivatives. Note that the elements of the gradient are multiplied by this alpha. Alpha can be understood as how large of a step we wish to take. So again, the gradient points us in the direction of greatest descent, and alpha dictates how large a step we take. Alpha is known as the learning rate. More on this later. So let's go ahead and update W and B. We have now landed on a new location on the surface, and we are closer to our goal of reaching the minimum. Note that a single step occurs with every backward pass. So when we visualize ourselves taking multiple steps along the surface, we are seeing the result of multiple iterations in the learning cycle. Now we repeat this process until we reach the bottom, each time calculating the value of the gradient for our current coordinates, then updating our weights and biases. Reaching the bottom suggests that the values of our model parameters are now set in such a way that the result of our model predictions incur the smallest cost. This in turn means our model parameters are set in such a way that the model predictions most closely approximate the ground truth target values. To solidify this image of gradient descent, let's take a look at a few more examples. Note that the shape of the surfaces will vary depending on the chosen cost function and the number of model parameters. All of the examples here are shown in three-dimensional space so that we can gain intuition about the optimization process. These examples happen to be in 3 dimensions because we are dealing with 2 model parameters, which form these axes, and the cost, which forms this axis. Since most models in the real world utilize hundreds, thousands, or even more parameters, the space in which these optimization computations occur would be impossible to visualize, to say the least. As a final note, Understand that there are some modifications and alternatives to the gradient descent algorithm, all with the goal of minimizing the cost function. We can see from this animation, which demonstrates several of these algorithms operating in unison, that some optimization processes behave differently than others, and may converge faster than gradient descent. In summary, we've understood the backward pass as a means of most efficiently updating our weights and biases in order to make incrementally better predictions. We've introduced the mathematical concept of the gradient in an intuitive fashion and understood that the gradient of a function points in the direction of greatest change in output of that function. Finally, we've understood how the gradient is used to most efficiently update our weights and biases through a process called gradient descent.